classroom video for WJC Maths A2 Unit 3 Pure Integration of Trigonometric Functions, which fits with the syllabus on section M2 3.7a. So we're dealing with trigonometric functions, and assuming that you know from your differential calculus work, and one of the important things is that if you want to be good at integration, you've got to really know your differential calculus. So we know that the differential of sine is equal to cos, and the differential of cos is minus sine. Keep in mind how that works. Obviously this section isn't going to deal with a proof of that. That comes elsewhere. And we also know that integration is the reverse process of differentiation. I won't insult you by talking about Wallace's rule or anything like that. So it follows there, because the differential of sine is equal to cos, it follows that the integral of cos must be sine plus a constant. And that constant is important. It's one of the most common places where students lose marks under exam conditions. You know that the differential of a constant has zero gradient, therefore it disappears when you differentiate. If we're integrating, we don't know whether it was there or not, so we put a constant in just in case. And that should be, unless you've got limits, your method. Doesn't matter what letter you use for that constant, as long as you're fairly consistent about it. Integration of sine functions, because of the fact that the differential of cos is minus sine, you've got to take a little bit more care. Again, one of the common mistakes is losing this minus signs. In fact, minus signs are probably the cause of most mistakes in mathematics. So the integral of sine x with respect to x is minus cos x, again plus a constant. And as I've said already, you must always add a constant of integration unless there are limits, and those limits, if we're dealing with trigonometric functions, must be in radian measure. So I want to quickly spend a bit of time looking at the negative sign issue, and it will be quick. So we know that integration distributes across the operations additions and subtraction. So we know that the integral of ax plus b with respect to x is exactly the same as writing the integral of ax with respect to x plus the integral of b with respect to x. And if I want to go further, I could actually say that that was exactly the same as a integral x dx plus b integral 1 dx. But that's probably taking things a bit far, because we're quite happy to integrate a constant without any real problem. So if I consider the integral of sine x in effect, the way it's written here, is a positive function. And we know that the way our mathematics system works, that we can consider the product of two negatives to be a positive. So therefore this is exactly the same, is identical to. You're used to that symbol there, it's congruent to, is exactly the same as minus bracket minus sine x with respect to x. And seeing as that distributes, I can take the minus sign outside my integration, so I get minus integral of minus sine x dx. Now of course the differential of cos is minus sine x, therefore the integral of minus sine x will be cos x. Hence I get minus cos x plus my constant. And I tend to use k for a constant, although you'll see in later slides that I actually change that depending on what I've got elsewhere. As I said before, it doesn't matter what constant you use, I'm quite happy for it to do so. If we now bring in the chain rule is a very useful piece of mathematics, differential chain rule, dead simple. Some people call it chain rule, some people call it function of a function. I personally call it Dido, differentiate the inside, differentiate the outside, or Dodi if you want to differentiate the outside and differentiate the inside. It doesn't make any difference. However you remember it, remember the chain rule, because it is a very useful piece of mathematics. So we know it applies to differential calculus, but we want to think about how it will affect our integration. And we know that the differential of sine kx, you notice I'm using k as a constant in here again, will be k cos kx, because the differential of kx is just k, so therefore it's differentiate the inside, which is the kx, gives me the k. Differential of sine bracket will give me cos brackets, therefore I'll get k cos kx. So if I consider the integral of sine kx with respect to x, now this is exactly the same as writing 1 times the integral of cos kx, 1 being a multiplicative identity, the thing that doesn't make any difference. And it's a very useful little tool, this particular introduction of 1. I'll use it again later on in some of the other slides. But 1, of course, is the same as k divided by k, or any other constant I want. But in this particular case, k is my particular constant, so therefore I'm going to use that. And then I can actually take the 1 over k bit outside, leaving me the bit that I know is the differential of sine kx. So therefore I've got the cos kx inside the bracket with respect to x. So therefore my integral of cos kx with respect to x is 1 over k sine kx plus some other constant. In this case I've used c. It doesn't make any difference, as I've said before. Similarly, by the same token, the integral of sine kx will be minus, because of the sine going to cos, same as I had on the previous slide, 1 over k cos kx plus a constant. Now, if I'm integrating between limits, we know that from our work so far that the area underneath a curve, or the area contained between a curve, the x-axis and the vertical limits, is given by the integral of whatever the function is, whether it be a y or an fx, between the limits with respect to x. Now that's because it's an area between the x-axis. If I wanted an area between the y-axis, it would be with respect to y. But that's not impossible, but it's just a case of swapping your constants over, or you can't swapping your variables over. So this is a little bit of graph from y equals sine of 2x, and my limits in this particular case are pi by 3 and pi by 6, and it's very common for them to use limits such as these, pi by 4, pi by 2, or multiples of those, because these are the values that you would be expected to know the exact values of in your trigonometric work. And ideally, in the best of all possible worlds, you won't use a calculator for this particular thing. So the integral between pi by 3 and pi by 6 of the sine 2x with respect to x. Now the integration is straightforward. Sine going to cos on integration will give me a minus creeping in, and as we had before, because the constant in front of the x is a 2, I'm going to have minus 1 over 2, or minus a half cos 2x between my limits pi by 3 and pi by 6. And I always use a square bracket. It doesn't actually matter what brackets you use per se. It's quite standard technique is to use a square bracket for these and to put your limits in. So therefore, if I put my upper limit in, which is the pi by 3, I'll get minus 1/2 cos of 2 times pi by 3, which I've written as 2 pi by 3. Doesn't quite matter how you write that. Minus my lower limit, which is minus bracket minus 1/2 cos 2 times pi by 6 is pi by 3. You notice that I've got a bracket between my two minus signs just to make sure I distribute that properly. Good technique. So this becomes the cos of 2 pi by 3 is minus 1/2. It's a second quadrant value, and in the second quadrant cos is negative. So I've got minus 1/2 times minus 1/2 minus 1/2. the cos of pi by 3 is also a half. If you think about it, that's logical because of the nature of the cos curve. So therefore I've got this particular function here, and the last time I checked, minus a half times minus a half gives me a quarter, minus times a minus a half will give me a positive half, times a half will give me another quarter, and a quarter plus a quarter gives me 1/2 unit square. So area underneath a trigonometric curve or between the trigonometric curve and an axis is a relatively simple aspect. The integration of the trigonometric function doesn't create any difficulty. One thing that you must take a little bit of care with is to consider the position of the curve when you're dealing with trigonometric functions, because we know from our work earlier on that the area above the axis is positive, but the area underneath the axis, that's the area below the axis, will turn out to be a negative. Now if you happen to have a root on your curve between your variables, you will actually have one part that's positive, one part that's negative, and therefore you will not get the right answer. So if I consider something like the integral between pi by 3 and minus pi by 3 of sine x with respect to x, then that's exactly the same as the integral between pi by 3 and 0 of sine x, because that's the positive aspect of the area, plus the absolute value, that's the positive response of the other bit, which is the fourth quadrant angle between 0 and minus pi by 3 of sine x. Or in fact I could have done it as 2 times the integral between pi by 3 and 0 of sine x by using the symmetry of the curve. So it's worth having a think about the actual shape of the curve. You can see clearly here that it's symmetric on either side, and my pi by 3 works quite nicely there. Now, it's possible for you to be asked to integrate the square powers of sine and cos. And in order to do that, you need to refer back to M2.3.5 C2, and that's your double angle formulae. Obviously, we know from our trusty WJAC booklet that the cos of A plus B is cos A cos B minus sine A sine B. They don't give you the double angles, which is a bit mean and nasty of them, but that's the way it goes. So since the cos of 2A is the same as the cos of A plus A, I'd end up with cos A minus sine A sine A, and the usual way of writing that is cos squared A minus sine squared A. I could have actually bracketed the cos A and had it all squared because it's the same thing, that's standard notation for it. So it's a relatively straightforward thing to do this. Now, you need to know these particular steps because they will help you if you ever deal with a question, and this would be a tough question, but it is possible. If you combine that with the trusty Pythagorean identity that sine squared plus cos squared is equal to 1 for all angles, then I can rearrange that quite happily to give me that sine squared equals 1 minus cos squared, or cos squared equals 1 minus sine squared. It doesn't make any difference, and I can replace either the sine squared or the cos squared in my cos 2a version, and therefore my cos 2a will become either 2 cos squared a minus 1, or the cos of 2a is 1 minus 2 sine squared a. It's a relatively straightforward substitution in there to get either one of those. Now, if I look at the second one, if I rearrange that, the moment I've got cos 2a is equal to 1 minus 2 sine squared a, so therefore if I twiddle things around, it doesn't matter how I do it, I could actually multiply everything through by minus 1 to make that positive sine squared. If I wanted to, I could swap it onto the other side if I choose to do so. It doesn't make any difference, but I'll quite happily get that 2 sine squared a is equal to 1 minus cos 2a, and therefore sine squared a will be 1/2 of bracket 1 minus cos 2a. And again, by the same sort of thing, cos squared a would be 1/2 cos 2a plus 1. Now these are the substitutions you need. These are not in the formula booklet, therefore you need to know how to develop them. I suppose it's possible that the question might ask you to deal with that in the first part and then use it to integrate, or, as I said, this would be quite a tough question because would be a lot of marks on it because you've got to develop quite a bit of mathematics to do so. But some people will be able to learn these things. Some people will have to develop them through. Now, if I then go to integrate between pi by 3 and 0 of cos squared 2x with respect to x, doesn't matter whether it's usual when we're dealing with calculus to talk in terms of the Cartesian xy values rather than other letters, but it doesn't make any difference. I can actually integrate with respect to any unit I want, or any constant I want, any variable I want. So I'm choosing again pi by 3 and 0, but you notice I've got a 2x in my element there. So if I use the fact that cos squared a is equal to 1/2 cos 2a plus 1, now seeing as in my particular case a is equal to 2x, double that, I'll get the 4x, so I'm going to get 1/2 cos 4x plus 1. Notice all the brackets going on with respect to x. My limits are pi by 3 and 0. Whip the half out. Not necessary, but you know, it makes life that little bit easier because you only have to deal with one fraction, or in fact possibly not even deal with it at all. Now the integration of the cos 4x, well, we should be hopefully getting our brains around that one by now. So it'll become 1/4 sine 4x. The integral of 1 with respect to x, of course, it is x. My limits are pi by 3 and 0. So I'll get 1/2 bracket 1/4 sine of 4 times pi by 3. God, that's rubbish 3, isn't it? Plus my value of x is equal to pi by 3, so plus pi by 3 minus. Now I personally, as an examiner, like to see the fact that that lower limit plugged in with the minus sign, because it shows I'm using my limits properly, does come to 0. We know that the sine of 0 is 0, so therefore 4 times the 0 is 0, so therefore I'll get 1/4 of 0 plus 0, which is 0 overall. Don't assume that's always the case, because you can think, if you think it through, you will get other ones that won't behave themselves as nicely. So now all I've got to do is know what my sine of 4 pi by 3 is. 4 pi by 3 is actually a third quadrant value, so sine will be negative in there, so you need to think about whether you've got positive or negatives. I know we're probably going to use a calculator for this. The old trusty ClassWiz is a useful device, but you must show these steps. So I'm going to get that half that was loitering out the front there. The sine of 4 pi by 3 is minus √3 over 2, but I've got 1/4 of that, so it's minus √3 over 8 plus my pi by 3. And yeah, I could multiply through by a half, but what's the point? It doesn't really make any difference. So I'm quite happy to deal with it and leave it in that form. I would personally normally perhaps underline that as an answer. So there are other trigonometric functions, but most of your exam questions will be based on sine kx or cos kx, or maybe even sine squareds or cos squareds. But as I said already, those are actually tough questions and require a lot of marks. It's possible to meet integrals of tan x's and cot, sec or cosec, which are the reciprocals of sine, cosine and tangent, not necessarily in that order. All the right words, not in the right order. So all of those functions require the recognition of log functions and will be addressed in a later video. And certainly the more common ones, the integral of tan x with respect to x and the integral of cot x with respect to x, those are the more likely ones to occur, and those are the ones that I will focus on at that time. And it's possible to integrate higher powers of the trigonometric functions. Excuse me. So, you could be asked, well, you can't because it's not within the scope of your syllabus, but at some later time in your mathematical careers, you will meet the integration of higher functions, and in fact, they use a combination of reversing the chain rule and the sort of substitutions that I've used earlier for the even powers.